Dear participants, we are glad to see you in remote mode at our webinar organized by National University Zaporizhzhia Polytechnic, Faculty of Computer Science and Technologies, Department of Software Tools, with Offenburg University of Applied Science, Germany. We are very glad to present you Professor Klaus Dorer, who is a specialist in area of artificial intelligence and robotics, and will say you interesting report about investigations in area of applications of artificial intelligence and robotics to the game of saucer. And I hope it will be very interesting for young people who are programmers, who are school children, who are students of colleges. We have a lot of people from different institutions registered for this event, not only from our department, but from the schools and colleges and some other universities. So I think that this event will be very important for us, not only in sense of international collaboration, but also to establish new contacts, to know something about interesting applications of artificial intelligence.
So thank you for this opportunity to talk to you. The talk has three parts. In the first part, I'd like to tell you something about RoboCup. This is the Robot Soccer World Championships. In the second part, I invite you to participate in some experiments when I explain what is difficult, why it is difficult to teach robots how to play soccer. And in the third part, I guide you a bit through the history of our team of soccer playing robots, what difficulties we're facing, how we over the years improved using artificial intelligence. So when in 1997 Kasparov was beaten in chess by Deep Blue, the artificial intelligence community was like looking for some new challenge. What could be done as a more difficult more difficult task. And the RoboCup Federation in 1997 came up with the idea to, by the year 2050, develop a team of fully autonomous humanoid robots that can win against the human world soccer champion team. And since 97, there are world championships of robots playing soccer. And as you can see from this little slide here, the World Championship is done every year, and it's done in many different countries. And in the meantime, it's one of the biggest robotics event worldwide with respect to the number of robots and also with respect to the number of participants. The Offenburg University is participating in this competition since 2009 in a 3D simulation league with simulated now robots. And since 2014 with the Sveti, our real robot that you see here on this slide. And I'd like to tell you a bit in the first part of this talk about this robotic competition, about this one of the biggest robotic events worldwide. So it's not all about soccer playing robots, it's also competitions in home robots. As you can see the images here. These robots compete in recognizing if people belong to this living room. The robots have to serve drinks to other people. They have to be able to open doors and close doors. So they interact in a living room environment. This is one of the leagues that are featured during a RoboCup. Then we have the Rescue League, robots that save people from earthquakes or from burning houses or whatsoever. So this is a competition setup where a disaster environment is created and the robots, some autonomously, some remote controlled, try to find survivors in this area. Then we have the industrial robots. It's a competition where robots compete in logistics, industrial logistics competitions. And like you see here in this image, with robots that can drive around and that have manipulators, and they have to perform tasks, and this is evaluated, and the best team wins. Also, the RoboCup is not just university, it's also about school age participants, where they do soccer playing or dancing with robots. So this is maybe one of my favorite leagues, the RoboCup Junior Dance, where you can see enthusiastic school children dancing together with their robots, in this case, the two flowers that you can see on the left and the right. And if you have a very close look, then you can also see that the second and the third school child are really not people, but are robots here that are dancing together with each other and are very enthusiastic in working. They have to program these robots and to build these robots on their own. And it's sometimes very hard to decide which is the best team. And then, of course, we have soccer robots. And I'd like to show you a different number of leagues. And I have to apologize if the videos don't work very well on Zoom. I hope it's working fair, but we will see. This is the small size league. These are wheeled robots. And these robots try to play soccer or play soccer on the field, 6 versus 6 in this case. And these robots they are not fully autonomous. There is a camera above the field which makes a camera image, a video feed to the robots. So the robots don't have their eyes on the robot, but above the field. And from the colored dot marks on top of the robots, they can distinguish from each other. So they will know which robots are in the own team and which robots are in the other team. And this is how they play soccer. I will start the video now, with the hope that at least some images get through in time. So the robots get their commands from the referee with Wi-Fi. And then they have to decide what to do autonomously on a remote computer, and this remote computer is then controlling the robots. Now, maybe a quick question is how many images per second do you get from these videos? Is it somewhat smooth, or is it very rough? Oh, sorry, I have to open the chat maybe. Oh, okay, that's fair. That's okay. So the next league is the mid-size league. These are fully autonomous robots, so all the processing power is on board, all the sensors are on board. These robots have to decide completely on their own what they will do. They are not remote controlled. And this is how the game looks like in this league. So they are playing 4 versus 4 on a bigger field than the small size league. And again, they have to decide on their own. They get the signals from the referee also by Wi-Fi. And then they have to try to score a goal, which is happening here. So very nice goal from the team. But again, these are wheeled robots. And of course, in 2050, when the human world champion has to be beaten, the robots would no longer have to be wheeled robots. So there are also legged robots in the RoboCup. This is the so-called Standard Platform League. In the Standard Platform League, 5 versus 5 now robots from the Aldebaran Robotics play soccer. Again, they are fully autonomous. All the cameras, all the sensors, all the processing power is on board the robots. They have to decide completely autonomously what to do. And let's see how this looks like. As you, as you can see, the robots, of course, sometimes fall down, but they are able to get up again and continue the playing. And uh, it's a very interesting challenge because you have to kick, you have to play. Very nice goal. You have to play together with your own teammates, and you have to, you don't know what the others will do, like in a real soccer game. Then we have the humanoid robots. They are also two-legged robots, and there are two sub-leagues, the humanoid kid-size league and the humanoid adult-size league. In the kid-size league, the robots are up to, I think, 60 centimeters high. They are self-built, they're different robots, so it's not a software competition like with the Now robots, where all the robots are the same. Here, the robots are different robots, and the people build them sometimes from scratch. And this is a scene from the 2022 World Championship in Bordeaux, in France, where the final of the game was done by Roban team from France and the CIT Brains. And guess who is scoring the goal? So you can see from the cheering of the people that it has been the French team which was scoring the goal. And this is also a league where all the robots are fully autonomous. All the processing power has to be on board. All the sensors are on board. And the robots have to decide what they do on their own. This is the adult size humanoid league, also a part of the game from 2022 in Bordeaux. They are playing 2 versus 2. And since the robots are so big that they will break when they fall down, a human operator is following the robot so that they can catch the robot in case of falling. And you can see this is still some way to go until the 2050 goal to play as good as human players. But nevertheless, they are also fully autonomous and also self-built robots of different sizes. Then we have the Soccer Simulation 2D League. This is a league where the robots are only simulated. And the advantage of this league is that we can play 11 versus 11 and the strategic level. The level on which you control these robots is very abstract, very high, so you can directly tell them to kick or to walk. So it's not like real robots where you control the motors, and you have very dynamic games. So a lot in this league is about strategy. Where do I place my robots? Where do I run to when I don't have the ball? Where do I pass the ball to in order to get through the defense line? So this was a very nice pass, and then the team was scoring. So this is a league where the focus is on strategy and artificial intelligence and machine learning. And there's another simulation league where we have now robots simulated, a 3D simulation league. And this is now physically much more realistic. So when this is the league where we participate in, you are controlling these robots by sending them motor signals every 50 times per second. So you have 6 motors in the right leg, 6 motors in the left leg. You have 4 motors in the right arm, 4 motors in the left arm, and you have 2 motors to control your head. And to each of these 22 motors, you're sending 50 times a second the signal to move, to bend the knee, to stretch the knee, and so on, so that the choreography of these commands will lead to walking, to kicking, and so on. The game we see here is the game between our team, Magma Offenburg, and UT Austin Villa, the University of Texas in Austin. It was the semi-final 22. And we were leading 1-0. A game is 10 minutes, so it was close to the end of the game, but this was a very dangerous pass from our opponents. As you can see, our defender is not doing quite well with getting up. But eventually, the goalkeeper was able to clear this ball with a kick. And we were able to win this game at that time with a score of 2-0. So from running from defense into offense is a very short time. So this is how it looks like when these robots play soccer, and I admit that there's ways to improve. But you may ask yourself, why is it so difficult to teach robots to play soccer? And this is my second part of the talk, where I'd like to invite you to participate in some of the experiments we will conduct. And let's start with the first experiment. So why is it difficult to teach robots to play soccer? Now, when we watched this game, we saw it from the outside. And that is not the case for the robots. They don't see this from outside, but they get their view from their camera like this. So my first little experiment is the question, through the eyes of which robot do we see this now? On the right, we see through the eyes of a robot. So which of the robots, 1, 2, or 3, we see? Through which eyes do we see? Yeah, on chat, we see already the answer. It's robot number 2. We see through the eyes of robot number 2. And that's right. And how did you know this? This is not a real question. I will. It's obvious somehow that the robot sees the other robot number 3 left and the ball and the goal. So it must be maybe robot number 2. It could be number 1, but here really it's robot number 2. But how do we know this? Well, what we do when we play soccer and what robots have to do when they play soccer is they have to know where on the field they are. So really, the robot has to have an idea of where on the field it is. So this is what the robot thinks. The blue lines indicate which area of the field the robot can see. So where the eyes are looking, so the robot is not able to see what's behind it. And from this, what it sees, like the middle circle, the corner flags, the goal, it has to conclude where on the field the robot is. We call this the robot has to localize itself on the field. This is one of the first tasks you have to do before you can successfully score goals. Now, I have a second experiment in which you can participate. It should also work online. I assume you're sitting on some chair or somewhere. And now I ask you to, for a short time at least, look away from your computer, look to some direction where you can see a bit further away, and then move your eyes slowly to the left and to the right. And if you do this, is there something that comes to your mind? Is there something special that you can observe? Or peripheral vision is one thing that is mentioned in the chat. Actually, yes, this is something that happens. That we are able to. We can't see very focused on the sides, on the peripheral sides, but we still see what's happening. It's not the thing I'm looking for. Actually, if you don't have an idea what I'm talking about, then the experiment was successful, because actually what's the thing here is that we don't recognize any specialties. This is what we do all the time. And why are we conducting then this experiment? Let me explain. This is the eye from above. Give me a second, I have to start the pen. This is the eye from above. And when you turn your eye to the left and to the right, then this image that is projected onto the eye is moving to the left and to the right. So the question could be, why does the image that we look at is not moving? And in fact, this is the case because your brain is doing something to you which is very beneficial. It calculates away this movement of the eye. How can it do this? By knowing where the eye is moving. So from the eye muscle, there is also signals to the brain that tells the brain how the eye is moving. And with this information together, the brain cares for that the room around us is staying still when we move our eyes. Now, I can prove this by a little experiment, but for this experiment, please promise that you stop when you get dull or if you get seasick. I have to stop after very few seconds, so it's a bit wobbly. So if you hold your left hand in front of your left eye, and then take your forefinger and put it between the eye and the nose, and then wobble. And stop if you're getting dull. So for me, it works when you wobble, then the eye is moving with your finger, and the image will move with it. So it's very strange, or well, not strange, but it's really that without the information of the eye muscle, how the eye is moving, when you move your eye in another way than it's expected to move, then the brain has no chance to recalculate that not the room is moving, but your eye is moving. And this is something we have to teach our robots. Again, the player number 2 is looking straight, and now the player number 2 will turn its head to the left. Our robots cannot move their eyes, but they can move their head, but it's the same thing for that. And if we don't tell our robots that it's moving its head, then it will assume that the field around it has turned. The world around it has turned. And this is not what we want. We want the robot to know that the world is not moving, but the robot is moving. So we have to tell it that the world is stationary and the robot's head is moving. Why is this important? This is, for example, important to know the ball speed. The ball will move quickly in the imagination of in the image of the robot, but we have to know that this is not a movement of the ball, but it's a movement of us. So the ball is really stationary. I have another little experiment. This is not so well working online, but you can do it, but you have to verify on your own how it's doing. So if you briefly close your eyes and then point to the place where the door is in your room. Of course, now you have to verify that you did succeed on your own. I'm betting that most of you have succeeded with this. And the question is why? How could you know where the door in your room is? I trust you. You didn't open up your eyes. You didn't probably hear your door. You didn't smell the door. How could you know? And this might sound to you like a stupid question, but it leads to something next we have to tell our robots. How did you know where the door is? Yes, exactly. Memory, visual memory. We remember this. We have something that is called a mental map. We know what's around us. And this is something our robots don't have from scratch. So once again, our 3 robots on the field. And now the robot number 2 looks to the left and sees for the first time robot 1. Before it has been out of view. Now it sees it. Without a memory, it will turn back its head and the robot is gone. And this is not what we want. We want that these robots remember where other players are on the field. So what we want is this. The player 1 is out of field, but we still remember that it has been there and it should still be there. Now my next question, it's not really an experiment. Experiment 4 is not working online, but a question will work. What has been the next thing we programmed into our computer, into our soccer playing robots after we have programmed them to memorize things? Immediately afterwards, we recognized that we have to do something else. Guess what? When a robot is able to remember things, The first thing you have to, well, actually, yes, we have to teach the robot how to get on different points on the field, but that's not something that's directly related to memorizing things. The one thing I ask for is that we uh, had to do something that is directly connected to memorizing things. Well, when you're able to memorize things, you also have to be able to forget things. That's the next thing we had to tell the robot, that after some time it's no longer useful, this information that it's remembered. You have to forget also things. So let's assume player number one has left the field for some reason, whatever. And without forgetting that it will still be in the mind of the robot. And after some time, this is just no longer useful, this information that there has been a robot 10 minutes before. So the next thing after remembering things is to forget things again. We want to have this after some time at least. And we have one last experiment, which is again, unfortunately not working in the online setup. But one last thing I want to show that we have to tell our robots is that they should be able to see what they don't see. And this is already something that only very few animals are able of. And of course, humans are. And what I mean is, let me explain. It's a bit difficult to explain, so I hope I will succeed. Let's assume our robot number two is looking to the right. So it knows, it remembers that there has been a robot one and a robot three. And in the meantime, while robot number two is looking to the right, robot three is moving back to the robot number one. And now robot number two looks back straight to the opponent goal. And this is what will happen if we don't tell it to see what it does not see. It will remember player one and it will remember player number three. And this is not what we want to have, because robot number two could know that the player number three cannot be there because it's looking there. This is, again, something very obvious and something very trivial for us humans, but we have to tell our robots, really, we have to tell it that if you look at some place and there is no robot, then it's not there. It should know that something that it can't see is not there. This is what we want to have. So these have been 5 examples of things we have to teach our robots. And there are really a couple more of these things. Like, for example, we have to tell our robots that it cannot run through other players. Very obvious for us, something you have to tell the robots. We have to tell them that it doesn't make sense to kick the ball when it's far away. So to trigger some leg movement in order to kick a ball is only useful when the ball is straight in front of that leg. We have to tell them how to get up. If we fail to do so, then the robot is lost for the whole game. Stupid things like, if the ball is in front of us, we have to walk forward to get closer to the ball instead of backward. Yeah, you see, we are able to play soccer with as little kids, because this is all very natural and very clear to us. And when you start to build robots that should do this, they need to know a lot of common knowledge we have to tell them. So we of course have to tell them that the ball should end up in the goal. I mean, in the opponent's goal, of course. That not all players should run to the ball, and then of course we have to tell them how to walk and how to kick with 2 legs. And this is the third part of my talk. I will guide you a bit through the history of how we teach our robots to walk and to kick with the different technologies and artificial intelligence, of course, to get better and better again. And all of this started in 2008 with our first walk. So here we really programmed, in Java, by the way, the robots to do motor movements like this. And As you can see, we managed to walk 2 centimeters per second, which is, of course, way too slow to play soccer. So we had to improve on this. And we came up with a programmed walk with 12 centimeters per second in 2009. And this was the first time when we participated in the Robot Soccer World Championship in the Robo Cup. It looked like this. 12 centimeters per second is fast enough to score goals. Yeah, so we scored a few goals. We have been one of the last teams of the tournament. That's usually the case when you start from new. But we even won one game. So it's 12 centimeters per second is okay. You have to imagine that this robot is about 56 centimeters high. So it's about 1/3 of a human. And this means that 12 centimeters, you would have to be multiplied by 3. So it would be something like 36 centimeters per second. Still much slower than a human, of course, but just to put it into perspective. 2010, we have improved already with 40 centimeters per second. And what we did is we no longer programmed each motor to do something, but we used splines and curves to control the motor movement so that it gets smoother and more controllable by us. And this was when we were able to walk 40 centimeters per second. Again, by sending 50 times each second to all of the 12 leg motors some signal to get it into a walk. This is still considerably slower than other teams have been at that time. So in 2012, we improved again with 65 centimeters per second. And the difference here is that we no longer did what we call forward kinematics to control the robot. We did no longer control the knees and the hip and the ankles directly, but we used the so-called model-based inverse kinematic walk. This means what we defined was the movement of the feet. So we only controlled the feet, and then we did a reverse calculation on how the knees, the hips, and the ankles have to move to put the foot in the position we want to have it. This is called an inverse kinematics move. And this improved our walk to 65 centimeters per second. Still some maybe 20% slower than the fastest teams at that time. And this is about how far you can get with programming. So we put a lot of energy in this, and we put a lot of fine-tuning, manual fine-tuning into the parameters of this walk, like how big the steps are, how wide we want to walk, how high we want to lift the foot. So a lot, say a number of 15 parameters that we can use to control this walk. And manually tuning them is something tedious. And that's why at that time we started to use artificial intelligence to improve our robots by, in this case, letting them learn these parameters through a genetic algorithm. I will explain in a minute how this works, but this improved our walk speed by more than 20%. And finally, in 2013, we arrived at a speed which has been at that time about the speed of the fastest teams. So we still use a model-based walk, but the parameters of this model are now learned. The robot is learning these parameters on its own. 1 year later, we were able to break the 1 meter per second mark with this robot. And I wonder how well, this is very difficult to see, but maybe you have an idea of what is different now. It's very hard to see. I have to tell you, it's hard to see. The robot has longer legs. Now you may say, of course, with longer legs, it's easier to walk faster. That's right. But when you use the walk that you have learned on a short leg robot and use it on a longer leg robot, it's actually slower. It's not completely falling down, but it's slower. So when we first had this longer leg robot and we used the walk that we had, the robot was much slower. But with artificial intelligence and with, in this case, genetic algorithms, it was easy to just retrain the robot. And then we were able to walk 1 meter per second with this longer leg robot. This has been the state of the art for many years. We didn't focus much on walk anymore, but we improved on strategy, on kicking, and so on. And then in 2020, we started to use another learning technique, which is called deep reinforcement learning. And this is a completely new world. So we still have the same robots, but we teach them to train a neural network. The input of this neural network is the current state of the robot. And the output of the network is the motor controls directly. So it's an end-to-end learning. And our networks are reasonably sized. Like we have about 100 neurons, input neurons for all the sensors the robot has, and about 28 output neurons that control the 14 motors of the legs. And this is how it looks like then. The robot is running 2 meters per second. And it's running like 2/3 of the time. Oh, sorry. 2/3 of the time, none of the two legs is touching the ground. And this is only possible if you have something that is controlling the robot in any state. This is the core difference between deep reinforcement learning and genetic algorithms. For genetic algorithms, you find one movement and you play this movement, no matter how the situation is. In deep reinforcement learning, you do the movement based on the current situation of the robot. So if the robot is a bit hanging to the left, it will have learned to do a different movement than it is if it's hanging a bit to the right. And this makes it a stable movement, and all of a sudden we had double the speed than before. I will come back to this in a minute, but let me first also show the history of kicking. 2009, we were able to kick 4 meters. That's already quite nice, but the time that it requires from decision to actually hitting the ball has been 5 seconds, which is pretty slow. Again, this has been a programmed kick. 2014, I'm jumping a bit here. We were able to kick 7 meters already and much quicker, 0.8 seconds. And we have been the first team that has been able to stop on one leg when walking and then kick directly. This is also still a programmed kick. And again, with genetic algorithms, we are able to improve this a bit from 7 to 9 meters and even quicker kick movement like this. So the robot is able to kick very quickly, and 9 meters is quite okay. And the question is, how does this work? Again, I told you this is done with genetic algorithms. So how does this work? Initially, we have roughly 50 robots that have a gene code. And in this gene code we encode how the robot is moving. And initially, most of these 50 robots will do any random movement, so it won't work very well to kick. So this third one has been a bit more successful. It didn't fall down, but all the others failed. So we will evaluate the movement, and the better robots reproduce with other robots. So the bad robots are thrown away. The better robots reproduce, create a new generation of robots with different gene codes. And after 10 generations of robots, the robot is already able to kick the ball. The task here, by the way, is to kick to the left side. And after 100 generations of evolution, the robots are able to kick to do what they have been asked to do. And this is about something that takes about 6 hours of learning. So doing the genetic evolution of 50 robots over 100 generations took us on our computer about 6 hours. And the big advantage of this is now that, by the way, one thing I have forgotten to mention is that we have one other robot here that has toes, that has one joint in each leg to move like toes. And this is something we are using for the kick to let the robot step on its toe, like, where's my pen? Like here, which improves the kick. So our toed robot is our favorite because it's kicking so wide. And why is this? How does this help? Well, sorry. We can tell the robot that kicking straight is good. Sorry, once again. We can tell our robot that kicking straight is good, and then it will learn to kick straight, as we can see here, a 9-meter kick. But we can also tell the robot that kicking to the right is good, and then it's able to do some right kick. So for this, we didn't have to change any software of the robot. We just have to have changed the trainer software that is able to evaluate how good the kick has been. Or we can learn to kick sideways. Again, the code of the robot does not change a single line. It's only the trainer that changes. Or we can kick backward. Or we can kick sideways, as we saw already in the last video. So this is a very big advantage of, of being able to learn, that we can train different things without having to change the robot anymore. We just change the training setup and the evaluation function. Now, when looking at this kick, genetically optimized, with respect to robustness, we can say that it's not so terribly robust. What we see here is on the x-axis, how much to the right of the robot the ball is. This is the middle of the robot here, and how far apart on the y-axis the ball can be. Like, yeah, it's actually this way around. So the green spot tells us if the ball is lying in this spot, then the kick will be successful, and if it's not in the green spot, then it will not be successful, and this will be a kick of the right leg. We can mirror this green area to the left for kicking with the left leg. And as you can see, this area is pretty small, so we have to be very precise on where to position the robot to the ball so that it will succeed in kicking. And there's been one thing which is particularly nasty, is that there is a blind spot here. So if the ball has been in front of the robot, we were not able to properly kick it, which is of course not very good. Also, when we have a look at where the balls end after a kick, so this has been the start position where the ball was positioned, and we kick to the right, and this is where 100 kicks ended. So you can see 9 meter is the successful kicks, but there are many unsuccessful kicks or very short kicks, and it's also a bit of a spread with all of the for the kicks. So it's not very precise at this time. And the kick is not flexible at all. When we straight kick, then we will try to kick 9 meters, not 5, not 3, not 8, 9 meters. And the direction is straight. And again, in 2021, we started to do deep reinforcement learning. And in 2022, we had a kick that is now able to kick flexibly in different directions and different distances with the same neural network. So again, we are back to a neural network. We have a deep neural network with with multiple layers that has been trained over probably more than 2 days. And after that, the robot is able to not only kick double the distance, like up to 20 meters, but also it's able to control how far it wanted to kick. So when you have a quick look on this video here, now it's an image. The red spot is where the robot was told to kick to. So let's see. So now it should kick 10 meters slightly to the left, and this is what the robot is able to do. And if you look closely, then you will see that the ball is not always on the same position relative to the robot. So the ball is on different positions. The robot is stepping in between and before, which is undeterministic. So it's now the ball is much more to the left than it has been before, and this is making it even more difficult. But still, the robot is able to kick pretty precisely to where we want to have the ball. So if you once again look at the genetic kick in the middle, and I call it PPO kick because that's the name of the algorithm we are using. It's deep reinforcement learning kick. Then you can see that the area in which we are able to kick the ball is much bigger. So we are much less dependent on where the ball is. We can still kick it because the robot has learned to do a different movement when the ball is further to the right. It has to move different to when it's further to the left. And this also makes it possible to kick balls that are rolling, that are not stationary on the field. So we are much more robust to the current situation. Also, when we look at precision, again, the kick has been 100. We did 100 kicks starting from this position to the right. And you can see that the kick is, first of all, much more distant. So here we ask it to kick 20 meters and 18 meters, and it was able to do this. And the spread is much less than with the genetic kick. Only 4 kicks were unsuccessful. And also with respect to flexibility, now we are able to control the direction and the distance. So on the x-axis here, you see the relative direction in which we want to kick. Plus angles to the left, minus angles to the right. And on the y-axis, you see the desired distance to kick, and everything that is green means that it has been quite successful. Yellow and orange means not so successful. So you can see that it's a very big area in which we are able to kick the ball. Now, what does this mean for playing soccer? We played 100 games with a team that was using the genetically learned kicks, and we played 100 games that we were using to play that were using the deep reinforcement learned kick. And from these 100 games, 96 games were won by the deep reinforcement learning team, and 4 games were drawn. Not a single game has been lost to the genetic kick team. So of course, as you can imagine, being able to kick twice as far is a very strong improvement. Now, to conclude this talk, I also want to show you some things that did not work so well, and also some lessons we have learned from teaching our robots to learn themselves. Let's start with walking. By the way, this is how it looks like when the robot starts to learn to walk with deep reinforcement learning. It does random movements, and it looks like this. It will fall over very soon, but it will get a reward when it doesn't, when it's moving forward or whatever. Now, of course, this sometimes leads to being a bit impatient. So when you look at this, then you can get impatient and you say, look, you want to help the robot and tell it, well, you have to move your leg forward. And we did this, and this is what happened. The robot learned to move its left leg forward, but it always did its left leg forward, and it was jumping on one leg, not what we wanted to have. And in another case, it went like this. Nico, who trained this, found this result on a Friday, so he called it sliding into the weekend. So this has been an abuse of a glitch in the simulator, And of course, this is not what we want to call walk. It's sliding on one of the legs, which is not allowed, of course, in games. Um, on the left side here, we wanted the robot to learn also to run backwards. So we did some steps of walk backwards, and then we wanted to start it to run backwards. And this is what happened. Again, not what we really wanted. And we were a bit surprised because we stopped the learning immediately when the robot is falling and give it a negative feedback. But here it seemed to not have worked, and we had a look at our detection if the robot is falling, and it was like when the torso, the upper part of the robot, is not upright, then we are fallen. And look how upright it is sitting down, so that it never triggers the fallen condition. In the middle video, David wanted to learn it to kick, but not like this. I hope you can see it, that the robot is really moving the ball with its support leg, the left leg, and we wanted, of course, to kick with the right leg. But after being so for this last video, we wanted the robot to kick from full walk, not to stop at the ball, but to run into the ball and kick it. But again, we wanted that it kicks the ball with the right leg. It learned that it's better to do one more step and then to kick with the left leg. So we let it kick with the left leg. One other thing that you have to be aware of when doing this kind of artificial intelligence learning is that in order to work in a real game, the training situation has to be very similar to what you expect in the real game. And this is one instance, one example where this was not working like we wanted to expect it. We trained the robot to get up quickly when it's falling forward, like this. And it learned to use its arms, and it learned to get back on its legs very quickly. This is slow-mo. So it's really a very nice get-up behavior that we have learned here. And we were curious to see how it works in the game. So we put it into the game, and it looked like this. The robot was completely unable to get up. Why does this happen? Because the robot was falling different than in the training. We were always falling the same way in the training, and when the robot is falling different, and then our learned behavior doesn't work anymore. Of course, also the weaknesses of a simulator are highly exploited. Like in the first case, we saw the sliding. Here, I think it's hard to see. The robot is beaming itself. It's using numerical instability of the simulation. It moves its toe in a way that it's almost exploding. The toe is flying away, and then it come back and is moving, tearing the robot some meters forward. Of course, this is not allowed in a game. Also, what's interesting to know is that with deep reinforcement learning, these behaviors that are learned, these neural networks that are learned, are very specialized to the robot it learned. So we have different robots here, one with toes, as I told you, and this is now a robot without toes, running the brain of a robot with toes. And this is how kicking looks like when a robot that has not been trained with the proper body is performing. It's not working very well, or not working at all, better to say. So this is very highly optimized now for a robot that has toes, and this one we see here does not have. So this concludes my talk. Let me tell you that this is a lot of fun to compete in this robotics soccer world championships. Here you can see our two teams, the team Magma, which is controlling the simulated robots I have shown you, and the team Sweaty, which is building and programming the robot that you see in the middle of this image. We have been quite successful in this RoboCup World Championship. The one thing that we are still missing in the Team Magma is a victory, a world champion title. We have another chance this summer in July when we go to Brazil to to compete in the RoboCup World Championship. And what I can tell you is that students very much like to participate in this project. So they participate voluntarily. They work on their evening times to improve our team. And what they do, and I can tell you that they learn much more than they would just learn in lecture, because they are learning to work in a team and they are learning to get something done at the right time. So the games are in summer and mid of July, and by that time everything has to be finished. So thank you very much, and I'm really hope I am ready to answer your questions.
Thank you very much, dear participants. If you have questions, please you can write questions in the chat, or you can say what we want. Please, if somebody want.
Thanks for the wishes.
Generally, it is very interesting, and I have several questions. Maybe I will ask before the people will think about their questions. When you make your experiments, you use only simulated environment and robots, or you have real, how to say, hardware. And what is this hardware? It's your own or commercially buy.
So the deep reinforcement learning, I was telling you, this is done on simulated robots. And there is work now in the research which is able to transfer this learning into real robots. So we saw already first experiments by other teams that learn this. For example, the Chinese T1 robot has been participating in a marathon, and the walk that they have been using for the real robot has been trained with deep reinforcement learning. In Offenburg University, we have this sweaty robot, which is here on this image. This is self-built. Most of the things are done at the Offenburg University, but that robot is for now only programmed. It's not using deep reinforcement learning for its movements, but it's of course using deep learning for recognizing the objects on the field, like the ball and the other robots.
If somebody other want to say something or ask, I can see only how to say general impressions, and many thanks to you. What technology stacks are used in the development? Is there a lot of constraints of CPU or RAM?
And that's a very good question. Thank you for that question. We don't have the RAM's requirements are very low. So really, we don't have any problems with using RAM. But you're right, we have quite some high requirements on CPU during training time. So what we do is when we train our robots, we don't train just a single robot, but we train multiple robots in parallel into the same network to speed up the learning. And still, it takes days to get a new behavior. So really, what we are always looking for is faster CPUs. We are not so much able to use GPUs, but CPUs is a requirement. During gameplay, the requirements is not so high. So I can run all the 22 robots of two teams and the simulation and the visualization on my notebook, and it's running not quite at real-time speed, but almost at real-time speed. So watching games or running games is not so CPU hungry. But it's one thing which is connected to this is that with the simulation leagues, of course, it's the easiest way to get into this kind of robot competition, because it's the cheapest with respect to participate. You just need your computer All the software that is used for this, the simulation software, is free to access, so everyone can access it for free. So you don't have any costs to try to run such games. And there is also some starting software available, so you don't have to start from scratch, that our team and also other teams present. So it's from all the robot leagues the easiest to get into this competition.
Okay, thank you. Maybe somebody other want to uh, ask something. I see only thanks for you. How do you think about improving your robots? Or maybe new features, if it is not a secret?
Well, your your question, very nice. You're right. We really have to sometimes be a bit secretive. We are open as much as we can. So I can tell you that we have been second last World Championship, losing against Portugal. And what Portugal is doing very, very well is the dribbling. So we are now trying to be more responsive to the dribbling of the Portugal team. Um, by, for example, being faster in deciding to kick and to kick the ball away. So yeah, sometimes we keep things secret, but one thing you also have to know is that after a World Championship, all teams have to publish their binary code. So as soon as you have participated, all teams can play against your team from last year. And this is what we do. We play a lot of games against FC Portugal from last year in the hope that they don't improve too much and we improve more than them. Um, like yeah, like kicking away the ball or being a bit quicker also with respect to movement.
We have also comments from Olga Hladkova. It's our teacher from our department. Thank you for your presentation. I have no questions. I have an interesting conclusion that this talk led me to, that we humans are trying to teach a robot to do something based on our experience. For example, to kick a ball with the right foot. For example, it can kick a ball with the left foot. Why not?
Thank you for your kind remark. Maybe one thing to this, we only train the robot to kick with the right leg. All the training we do is with the right leg. But we are, of course, or not of course, but we are able to mirror this kick to the left leg. So once we have learned the kick for the right leg, we mirror all the observations and all the actions to the left leg so that in the end we are finally also able to kick with the right and the left leg. And of course, still when being able to kick with the right or the left leg, we still have to decide which leg to take in the current situation. So this is really something we also have to tell our robot that it should use its left leg when the ball is in front of the left leg and its right leg when it's in front of the right leg.
Do you want to cooperate with world leaders in robotics to do your future projects?
Yes, this is in fact what we do. So you saw our sweaty robot, and it's quite expensive to build such a robot. And we built this we started in 2014, and we improved it all the years. And still, as a single small university, Offenburg University is considerably smaller than Zaporizhzhia Polytechnic. So it's very hard to keep pace with the industrial leaders. So what we do now is we buy robots that you can buy from scratch. So you just buy the robot and then we start on on a software level to learn to teach them how to learn to kick and so on. So this is what we did with one robot now. It's a T1 robot from a Chinese company, and yeah, it's interesting to see that these robots are getting cheaper and cheaper. So it's much cheaper now to buy a robot than to build one from your on your our own.
The next question is, how do you think will the robot be able to outperform a human in football in the future?
This is the question I was actually prepared for. This is the question that is commonly asked. I'm with RoboCup since 1999. So the first time I participated in RoboCup has been in 1999. And it's very, very interesting to see the progress over the years. So when I showed you the videos, it didn't look like too human-like soccer playing, of course. But when you see it year from year to year, you see the big progress that is made each year in all of the leagues. Now, but it's just only 25 years until we are at the year 2050, where we want to win against the human world championship champion. And I think it's a very long way to go. It's I can't say that I don't believe in it, but it will be a very long way to go to be as successful as human players. Let me just point out one or two points. One thing which is turning out to be quite interesting is that humans are very energy and efficient. So one of the questions really open is that how can we provide these robots with enough energy to run for at least 45 minutes without having to change the batteries? So this is something that we can observe that humans are very energy efficient. And of course, what it's not a goal is to create robots that are twice the size of a human and just uh, are faster because of that. So really, the team should be an accepted team by the human players as an opponent, not using some fancy robots that can run twice as fast because they have double the leg size or something. This is not the goal. So how can humans be outperformed? Well, it will be interesting to see how this can happen. 25 years are still to go.
Uh,
Sim
Here somebody want write, what simulation programs do you use?
the simulation that is used in 3D simulation is a self-created simulation. It's called SimSpark, and it's based on the ODE, Open Dynamic Engine physics simulation. That's one simulator we are using. One other simulator we have been using is the WeBots simulation for our sweaty robot. And now we are also looking into the Mujoko simulator, which is a very popular simulator for the deep reinforcement learning community. So these are the three simulators we are actually using: SimSpark, Mujoko, and WeBots.
Thank you. And I have a question. The real robot in the physical world need to take into account how to say different physical aspects like how to say mass and of ball of its body, the movement, different procedures, etc. You use how to say a model which take this into account by software, or you need to take it this into account by your algorithms too.
This is
So
this is done on the thing. Sorry.
your algorithms is only how to plan robots actions without taking a physics into account, or you also take real physics into account in your
It's it
algorithm.
Yeah, sorry. It's tried to use real physics. So the SimSpark is simulating real physics to some degree. And that's why we're moving um, more and more to other simulators like Mujoko, for example, because they are more realistic in simulating. So in SimSpark, we also have the mass of each body part. We have a maximum power of each motor. So a couple of things are simulated quite physically realistic. But for example, how the robot touches the field is very much more forgiving in a SimSpark simulation than on a real robot. Yeah, when you program a real robot to walk, you will see that the kind of surface you're walking on makes a big difference on how the robot is walking. And this is somehow simplified a bit in the SimSpark simulator, so that's why our robots don't fall as often as the real now robots, and that's also why we can walk considerably faster in the simulation than with the real now robots. So there is a try to get the simulations as physically realistic as possible, but also to keep the balance, also to the that we can run 22 players on one computer in real time. So this is a trade-off.
Mhm. Thank you. The next question is, how long will it take to build one robot?
Well, that's a good question. To build a real robot, it takes years. I can tell you it's years. So you have to really construct it. You have to sorry. For real robots, you have to construct it mechanically, you have to construct it electrically, you have to program it low levelly, hard level. So this took us 2 years to build a robot, and then we had to improve it from year to year. For the simulated robots, it's not so bad because you can download um, base code. We call it base code that is already doing a lot of communication with the simulation, which is already, most of the base codes are able already to walk, not so fast, but you can improve it. So that is something you can get into within weeks, I would say. So if you consider to participate in such a competition, then it would be hard for you to. It's already too late for this year because the qualification also has been running. But for 2026, this would still be possible, fairly easy with simulated robots, and it would be quite challenging to do this with real robots for next year.
Okay, the next question. I have seen robots that repeat the movements of a human assistant in a presentation. What technologies are used to reproduce the movements of a human assistant? What are the further studies in this direction?
What you probably talk about is motion capturing, that we can record the movements of humans with motion capture technologies like they do in films, to get them to work on robots. We have done some experiments with this, and um, we have two results from this. The first one is that it does not work on real robots one to one. So if you record a movement with a human and you play it on a real robot, it will fall down. It's simply because you you have to react to the current situation, to the physics. So when you record a movement, the human might have been walking straight, but the robot might slightly lean to the left, and then it will just replay what you have recorded. So this does not work well. But when you do this motion capturing, you can use it as a starting trajectory for your learning, so that you don't learn from scratch without any knowledge, but you say, this is the movement I want to have, and you start from that movement to improve it. This is something where you can use motion capturing.
The next, we have several other questions. Uh, uh, I wonder if a robot can get a red or yellow card from a referee.
That's a very good question. Thank you. Yes, in fact, in our league, no, we don't have red or yellow cards. We have fouls, but the robot are then beamed away and can just run back to the field and can continue to play. But in real robot leagues, they have yellow and red cards. So if a robot does a bad foul, it gets a yellow card. And if it repeats to do a bad foul, then it gets a red card and can no longer use during this game, like in real soccer.
Thank you. And the next question. And what about obstacles? It is also a difficult task to the saucer player.
That's right. Yeah. I told you that we have to tell our robots that they cannot run through other robots. The truth is that we are particularly bad in avoiding obstacles. We're looking to run around or to walk around obstacles, but when our robots are running, they are so fast that they are not planning enough ahead currently, so they crash sometimes into each other. This is
Mhm.
something we can slightly ignore in the simulated robots, but in real robots, of course, you cannot do that. They will be damaged.
And the next question. What microcontrollers are you using?
Well, for the simulated robots, none, because they are just simulated. Don't ask. I don't properly know. It's some NVIDIA CPU on a sweaty robot. We have some NVIDIA CPU GPU combination, which is very or very powerful, but very energy efficient. I can't really tell you the proper name of it.
Okay. Uh, I can not see any other questions, so we are very thank you for your presentation and for your answers. I hope that our participants will be very happy. And I also want to thank you for your support of our community, because in the work conditions it's very important for us to keep contacts with foreign scientists, and unfortunately now it's not so safe to come to our city, but we hope that in future you will have such possibility, and we have many possibilities to visit European countries. So today in virtual mode, we in remote mode, we have communications and such lectures and workshops, very interesting for our students, for our teachers. So I have many thanks for you for your support, and I hope for the collaboration with us. So thank you very much, and participants who visited our webinar, and I hope that in future we will propose you any other webinars with Offenburg representatives and other scientists too. Thank you very much all.
Thank you, and I hope that it's the near future we talk about when I can come to Zaporizhzhia.
You're welcome. So
Thank
bye-bye.
you.
Thank you very much, everybody.
Goodbye.